In heat, we know that both heat and work correspond to transfer of energy by some means. By some means, the idea was first applied to the We know that both heat and work correspond to transfer of heat by some means. The idea was first applied to the steam engines where it was natural to transfer heat in and get work out. Consequently, it made a sense to identify both heat is and in and work out as positive quantities. Hence, work done by the system on its environment is considered positive, while work done on the system by the environment is taken as negative. If an amount of heat Q enters the system, it could manifest itself as either an increase in thermal energy or as a resulting quantity of work performed by the system on the surrounding or both. We can express the work in terms of directly measurable variables. Consider the gas enclosed in the cylinder with a movable frictionless piston of cross-sectional area A. In equilibrium, the system occupied volume V and exerts a pressure P on the walls of the cylinder and its piston. The force F exerted by the gas on the piston is Pa. We assume that the gas expands through delta V very slowly so that it remains in equilibrium as the piston moves up through a small distance delta Y. The work W done by the gas is W equal F delta Y equal Pa delta Y. A delta Y equal delta V change in volume. A gas sealed in a cylinder by a weightless frictionless piston. The constant downward applied force F equals Pa, and when the piston is displaced downward, work is done on the gas. The work done can also be calculated by area of the curve under P minus V graph. Knowing the details of the change in internal energy and the mechanical work done, we are in a position to describe the general principles which deal with heat energy and its in transformation into mechanical energy. These principles are known as law of thermodynamics. 11.4 First law of thermodynamics: when heat is added to a system, there is an increase in the internal energy due to the rise in temperature and increase in pressure or change in the state. If at the same time a substance is allowed to do work on its environment by expansion The heat Q required will be the heat necessary to change the internal energy of the substance from U1 in the first state to U2 in the second state, plus the work W done on the environment. Q equal U2 minus U1 plus W. Q equal delta U plus W. Thus the change in internal energy delta U is equal U2 minus U1 is defined as Q minus W since it is the same for all processes. Concerning the state, the first law of thermodynamics thus can be stated as in any thermodynamics process when heat U is added to a system, this energy appears as an increase in the internal energy. Delta U stored in the system plus the work W done by the system on its surroundings. A bicycle pump P is a good example. When a pump on the handle rapidly, it becomes hot due to mechanical work done on the gas, raising thereby its internal energy. One such simple arrangement is shown. It consists of a bicycle pump with a locked outlet, a thermocouple connected through the blocked outlet allows the air temperature to be monitored. A piston is rapidly pulled. Thermometer show a shows a temperature rise due to increase of internal energy of the air. The push force does work on the air, thereby increasing its internal energy, which is shown by the increase in temperature of the air. Human metabolism also provides an example of energy conservation. Human beings and other animals do work when the walk, run, or move. Work requires energy. Energy is also needed for growth, to make new cells, and to replace old cells that have dead. Energy transforming processes that occur within an organism are named as metabolism. We can apply the first law of thermodynamics. Delta U is equal Q minus W to an organism of the human body. Work W done will result in the decrease in internal energy of the body. Consequently, the body temperature or in other words, internal energy is maintained by the food we eat. Isothermal process in a process it is a process which is carried out at constant temperature and hence the condition for the application of Boyle's law on the gas is fulfilled. Therefore, when gas expands or compresses isothermally, the product of its pressure and volume during the process remains constant. If P1, V1 are initial pressure and volume, whereas P2, V2 are pressure and volume respectively, after the isothermal change takes place, then P1 V1 equal P2 V2. Isotherm isotherm constant pressure. In case of an ideal gas, the the P potential energy associated with its molecules is zero. Hence, the internal energy of an ideal gas depends only on its temperature, which is which in this case remains constant. Therefore, delta U equal zero. Hence, the first law of thermodynamics reduces to Q equal W. Thus, if gas expands and does external work W, an amount of heat Q has to be supplied. Thermal change, since transfer of heat from one place to another requires time, hence to keep the temperature of the gas constant, the expansion or compression must take place slowly. The curve representing an isothermal process is called an isotherm. 11.16 thermocouple, trapped air in pump, piston pushed in, millivoltmeter. Heat, for your information, heat positive system positive Q, minus Q system heat negative system negative work, negative system W minus W, plus work plus W system work positive. mm, P P 11 constant pressure. The gas sealed in a cylinder by a weightless frictionless piston. The constant downward applied force F equal Pa, and when the piston is displaced, downward work is done on the gas. 11.2. mm, Look here.